Hello class, this is going to learn about area. So first, I'd like you to try to answer this question. What is area? You can put that in your own words, and here are a few bullet points to help guide your answer. So pause the video, and we'll go on together. So we're going to come back to this question shortly. First, I'd like to look at a couple examples. We have a rectangle that measures 3 units by 5 units. What is its area? Well, hopefully you remember that area of rectangle is length times width, so 3 times 5, 15 square units. What about this rectangle? It measures 3/4 by 5/3. Well, same idea. Just multiply them together. You get 15/12, which simplifies to 5/4, right? GCF here is 3, so that's our answer. So now the big question is, why does this work? Why can we use that formula to figure out the area of a rectangle? Particularly, we only looked at whole numbers and rationals so far. So let's see. First, area. Area essentially is talking about how much space does a figure take up. We don't care if it's a rectangle, a circle, some complex figure. How much space does it take up? And to quantify that space, we want to talk about how many unit squares, so 1 unit by 1 unit squares, can we fit inside of that region. So in the case of our first rectangle, right, it's 5 units in one direction and 3 in the other. So you can think of it as repeated addition, 5 plus 5 plus 5. But we know repeated addition is just multiplication, so 3 times 5. So that's why this formula works when we have nice whole numbers. Now what about our fractions? Similar idea, but now we got to break up our unit square. So we multiply these and we know we get 15 out of 12. So that's really saying that we have 15 rectangles where each rectangle has an area of 1/12 of a unit, of a square unit. So to make those rectangles, you would split up a unit square so that you split it evenly into thirds in one direction and evenly into fourths in the other. So each rectangle has an area of 1/12 of a square unit. And to represent the area for this rectangle, we would just put 2 of these side by side, and we would shade 3 of the rectangles in one direction and 5 of them in the other. This is 3/4 times 5/3. If you count them, we have 15 little rectangles, and each rectangle has an area of 1/12 of a square unit, so 15/12. So now the question is, what happens with irrational numbers? What do you think the area of this rectangle is? Well, you can go with the same argument, right? You just want to multiply them together, multiply those 2 dimensions, so you get square root of 6, right? Multiply radicands together. If you do the decimal approximation there, 2.449, etc. Now the question is this a precise answer? Right? Before we had a precise answer. It was a nice rational number, nice, even more specific, we had a nice integer when we had 5 times 3. Is this a precise answer, though? Is this exact? Well, square root of 6 is exact, right? That encapsulates the entire number. But anytime we try to write out the number as a decimal, we come to a problem because we're always approximating it. We can't write out every single digit. It's an irrational number, right? It never ends, it never repeats. So we can't be precise like we were before. So can we use an explanation like we did before with the fractions for our irrational numbers? Now, we really can't make that argument because whenever we try to write an irrational number as a decimal, it's an approximation. We can't write it as a rational number, obviously, and decimals don't get the job done. So we can't really make the same argument. But there's a different strategy we can use. And it involves something that we're not going to talk about explicitly, but it's involving something called a limit. So we're going to see what happens when we take approximations and make them better and better. So here we have a decimal approximation of square root of 2 and of the square root of 3. And one way to do it is you want to figure out, okay, well, here's the exact area, this rectangle. What if we figured out the area of a rectangle smaller than it and the area of a rectangle bigger than it? Because then you know the area has to be sandwiched in between the two. So for example, if we were to say approximate using integers, right? So we would cut off this number after the 1, right? So we'd, it's like the floor function, right? We go down to 1. And the same for the square root of 3. So we'd have a 1 by 1 for the lower approximation, which would give us 1 times 1, 1 square unit. Now if we want an upper approximation, Similar idea. But now we're going to use the ceiling function, right? So it will be 2 and 2, right? Because that's the integer, next integer that's greater than this number. So it'll be a 2 times 2, 2 by 2, and then you get 4 square units. So you know the actual area has to be somewhere in between those two numbers, which is nice, but could we do better? Yeah, what if we took our approximations out to the 10th place? So for the square root of 2, we would drop everything after that 4, and for the square root of 3, everything after the 7. So a lower approximation would be 1.4 times 1.7, 2.38 square units. And if we go the other direction, up, our upper approximations will be 1.5 and 1.8, which gives us 2.7 square units. And notice that these rectangles are closer to the rectangle we're looking, that we're trying to find the area of. And these are rational numbers, so we know that this process works. All right, but could we do better than this approximation? Yeah, if we took it out to the thousandths place. Now, in the picture, it's really hard to see the difference between the rectangles, but if you zoom in, there is a space, there's a little sliver on both sides. And if you crunch the numbers for these, there is our lower area and the upper area. So the idea is we can keep repeating this process, and we have an infinite amount of digits, so we can keep on doing this and getting better and better answers. So what's happening in the first column here? What's happening with these numbers? We're just doing more approximations of the square root of 2, but every approximation is less than the square root of 2. Okay, and what about the second column? It's the same idea. You have approximations of the square root of 3, but they're all less than the square root of 3. Okay. And what do what effect do these have on the area as we keep going down? What happens to the area? Well, we started off with 1, then we got 2.38, 2.4393, etc. Well, it's getting more and more precise, right? Getting closer to what we're looking for. And so what do you notice about the decimal expansions over here? What do you notice about these numbers in the products? What's happening to them? What's special? Well, the more digits we use over here for our approximations, the better our estimate gets, and these numbers at the beginning start staying constant. So here we have 2s, and then after a little bit we have 4s in the 10th place, and then 4s in the 100th place, and then 9s in the 1000th place, etc. So more of those digits stay the same. And what about our, let's see, I'm sorry. So if we're looking at the square root of 6, how does that number on the calculator relate to our products? Well, those are getting closer and closer to the square root of 6. Right? The more precise we are, the closer we get to this number. So what does that square root of 6 have to do with our square root of 2 and square root of 3? That's the product, so we just multiplied. So in this table, we had underestimates everywhere. So what happens when we look at the overestimates? So these are all greater than our square root of 2 and square root of 3, or 2 dimensions. So let's see, does the relationship with the square root of 6 still hold here, like we had in the other one? What happens with these upper approximations? Yeah, they're getting closer and closer to the square root of 6, but now we're going in the other direction. We're more than the square root of 6, and we're getting closer and closer to it by going down. So in our first table, we have estimates that are less than our area, and in this table, we have ones that are greater than our area. And if you continue this process as far as you could, infinitely many times, there's only one number that satisfies these conditions. The square root of 6 gets sandwiched in between both tables. So now this argument tells us that the area of the rectangle is indeed the square root of 6. It's the only number that satisfies these conditions using this process. Like I said before, this is something called a limit. We'll learn about it more in future math classes. But we're just doing something a whole lot of times that's getting close to our exact answer. So here we have an ellipse. And we want to see, can we estimate its area using a similar method? So say you want to cover this with paint, and each paint can covers 1 square unit on the plane. How many cans would you need to cover the entire region? Well, how many full squares could you fill in? And how many half squares could you fill in inside this region? So for example, what do I mean by that? I mean, if we took a square, let me fill it in. So here's an entire square we could fill in right here. So that's one. Okay. We could also do a half square. If we look over here, we can't do the entire square, but we could go on the diagonal here, and we have a half square. We can shade that in as well. So see if you can repeat this process and see how many squares and half squares you can fill in inside this ellipse. Okay, so if you do this as much as you can, you should end up with a picture like this one. And if you're careful and you count all of the full squares, right, those are each one square unit, and then for each two half squares, you have another unit, you end up with 34. So you need 34 cans of paint if we're trying to fit all of these inside it. So this would be our lower approximation. So what if we did it the other way around? What if we went with upper approximations? So in this case, we're going to cover as much as we can without going too far away from our ellipse. And how many cans of paint would this take? Well, if you counted carefully, you would have 52 cans of paint. So in order to get an approximation, we can take the average of our two answers, and that would be 43 cans of paint. Okay, but we could do better than that. How can we improve the accuracy of that number? We could use smaller squares. Use smaller square and half squares. So we're not going to go through this whole process, but this is what it would look like if you use smaller ones. These would be it's 1/2 by 1/2, which would be a quarter of a square unit. And then the half squares would be 1/8 of a square unit. And if you cut our estimates, they get closer together. Now we have 41 and 51, and the average there would be 46. And we haven't learned this formula yet, but it turns out that the exact answer is 15 pi, which is about 47.12. So this is the unique number that if you were to continue this process forever and ever, that's the only number that gets sandwiched in between the two approximations. And here are some common area formulas that you should know from previous grades. So we have the area of a square, rectangle, parallelogram. I think there's all cases of the parallelogram formula, but just written nicer for the special parallelograms. Triangle, trapezoid, and circle, of course, pi r squared. Rhombus and kite, maybe you haven't seen these before, 1/2 the product of the diagonals. These aren't as common as the other ones, but you should still know them. So in this lesson, we learned about area. We learned its definition and how we can approximate it by using unit squares. Thank you for watching this video.